Hello and welcome back to Calculus 1 section 3.9 Exponential and Logarithmic Differentiation. Well, logarithmic differentiation is a part of this. Derivatives of exponential logarithmic functions and logarithmic differentiation. Good. So we dealt with polynomials, some kind of rational expressions. We dealt with trigonometry. And now it's time to dig deeper into exponential functions and so on. So what am I going to do first? First, we are going to take a look at basic exponentials. So let's first look at stuff that we already know, right? Oh, thank you. I got concerned. Before we do any derivatives, I will remind you of the limit for e. So number e is defined as the limit as x goes to infinity of 1 plus 1 over x raised to the x. And this can actually be used to, in the definition of the derivative, in the limit definition of the derivative, to figure out that the derivative of e to the x is e to the x. And for honors section, right, that's a standard problem for exam or something. So those of you who are regarding themselves as more advanced, please use this and derive e to the x derivative from using the limit definition. So this is the definition for number e. And now you will frequently see later in calculus, Calc 2 especially, but also DiffQ and so on, situation where you have e is equal to the limit x goes to infinity of 1 plus, and then you have some p over here over x raised to the x, and that is actually just equal e to the p. So you can have the exponent there. Another modification would be, let's say, e to the r, where the limit x goes to infinity of 1 plus 1 over x raised to the rx. Now all of these get to work together when you have, do you remember those continuous compounding formulas and things like that from pre-Calc 1? Yeah, I know it was like 17 years ago, but maybe you remember it, no? Where the amount was equal to the principal 1 plus r over n raised to the nt. And then there was the continuous compounding a equal e p rt. Now if you look closely at these two equations, you can see the form, and this r and p like being your n and t from the other equation. So r, n, and t. Now that's a little bit with limits, just a few definitions and then application, like where you would have continuous compounding, which means compounds forever, at every moment, I'm sorry. So now we're going with derivatives of exponential functions. So first of all, exponential function is defined as y equal e to the x, or y equal e to the f of x, or y equal b to the f of x as the most general case you can have. So, this third case could be y equals 3 to the sine x, Okay? You can have that. And it will be fine to take the derivative because we are going to learn the formula for this. And it's going to be very simple. So what are the formulas that are taking care of all of these derivatives? Well, the derivative of e to the x is your good old e to the x. Then we upgraded with a chain rule into e to the ax to be a e to the ax. And then we upgraded with the chain rule with a whatever function you can plug up there, get e to the f of x times f of x prime. So these are the three that we have so far, that we learned so far. And clearly the one on the bottom is the most general one because it contains all of the formulas above. For instance, if your f of x is equal to x, then the whole thing collapses to the first line. And you can see that because f prime would be just 1, and you will just have e to the x. So it's good, right? So all of these formulas hold, where this one is the most general case so far. But as I said, the actual most general case is when your base is not e. You can have any base. For instance, base 10. That's okay, because 10 to the 0 is 1, 10 to the 1 is 10, 10 squared is 100, 10, right? This is 10 cube is 1,000, right? So it actually gives you the decimal system. So you can have base 10, that's okay. Base 2, binary, right? So you don't have to have just a base e. So what is the derivative of the most general case that we can get? It is the derivative of b raised to some function. As I said, like 3 to the sine x. So what is this? It is b f of x times f prime of x times ln b. And this, I'll put on a cloud. This is the most general case that you can get for your exponential functions. Now, is this backwards compatible with everything you learned? Sure it is, right? What is the derivative of e to the x?
E to the x.
Oh, well, thank you. Let's plug everything in the formula. So comparing these two forms over here, I get that b is equal to e, and that the f of x is equal to x. So now just plug that everywhere on the other side. So b is e, okay, f of x is x, times the derivative of x is 1, times ln of b, which is ln of e. Well, that's 1 as well, and you get your e to the x. So it works. This formula, which obviously, if you're interested, you will prove, right? This formula is the most general exponential case that we can get. And with that formula, we can compute anything in terms of exponential functions. So let's start. I mean, this derivation is not that important, so I'm just going to get rid of it. And let's practice this. So what is the derivative of the problem I said? 3 sine x. Go. So 3 raised to the sine x. What is the problem? I mean, the answer.
Should reverse these Calc 1.
I've done 89 settlement yet. I can't do this.
Let's take a look at this problem together. So clearly b is 3, f of x is sine x. You just plug everything in. So we have 3 to the sine x times the derivative of the exponent, which is cosine x, times ln 3. There's nothing that you can simplify over here. That's it. So just walk away. That's all it is. Hope you're not disappointed. So one more example, and we are done with these guys. So 1/5 raised to the, I don't know, negative tangent squared x, whatever. I'm trying to make it like the worst possible thing ever. And then I failed. I just noticed it. From where?
Off of my life. There's a few chapters like or sections missing.
Yeah.
I'm trying to do it. So
Will do.
if you want to reopen 3, 4, and 3, 5, that'd be awesome.
Yeah, that'll
get some extra practice.
Sure, no problem.
Thank you very much. You're the best.
Just have some flakes over here. Yeah, it's okay. I will. 3, 4, 3, 5? Okay.
Thank you.
For a donation, right? Good luck.
I already did it. I just want to do some more practice. You know? This comes down steady. Shut up.
Let me check. You say you did it?
Yeah, you can check.
Yeah, you can check.
I didn't do a lot of it, but something's done. Something's done.
All right, so let's take a look at this problem. By now you probably figured out that I put a negative exponent, and if you put the negative exponent, guys, and you having to redo your hair because of him, it does not concern me at all. So, so you might have to, as a collateral damage, yeah, you might have to move. It goes for the first row as well, so yeah. So the negative exponent is going to flip the fraction, and when the negative exponent flips the fraction, we just lose the negative on tangent. So that's what we have now. And we follow the formula. So copy as is. So tangent squared x. And then the derivative of the exponent, which is 2 tangent x, and then derivative of tangent is secant squared x. We have the chain rule there. And then times ln 5. Yay. Yeah, that's it. I hope you're not disappointed. Oh, what's the derivative of e to the pi? 0? Why? Pi is a constant. Nice. E to the pi is just, it's like 3 squared, okay? I mean e to the pi. So, yeah. Maybe, should we write that down? Okay, the derivative of e to the pi is 0 because it's a constant. Now if you want to use the formula, you can. It's derivative of e to the pi times the derivative of pi, which is 0, and that's what kills it. Oh, you're not going to stick for logarithmic differentiation?
Oh wait, when is that start?
No. The next 30 minutes. So time for log stuff. Yeah. Yep. Logs. Good log? I think it's a good log. Logs. So I have to go through the entire spiel on logs because you guys in Calc 1 tend to be not too familiar with this stuff, even though this is pre-Calc 1. So I'll start at the beginning, review everything, and then we'll do calculus portion of it. Fair? So let's start first with some cool stuff. How much is 2 plus 3? I see some issues. Now we can recover both 3 and 2 if we use the opposite operation, which is very good. So how much is 5 minus 3? Good. And how much is 5 minus 2? Nice. Okay. Thank you for your participation. Now we are going to up the stakes. We are going to move from addition into a fast repeated addition, also known as multiplication. So, 2 times 3 is? And then 6 divided by 3 is? And 6 divided by 2 is? Great. So, there we go. Now I'm going to go from fast repeated addition to an uber fast repeated addition, which is actually repeated multiplication, which is exponents. So how much is 2 cubed? Very good. Now I can clearly recover 2. If I go cube root of 8 is 2. How do I recover 3? How do I recover 3? Is it a square root? No, it's not a square root. Log. So log base 2 of 8 is 3. Do you see where the log fits? It's just calculation, right? It's like addition or subtraction, except it has letters. It doesn't have a cute symbol, right? It has 3 letters, but the concept is the same. You are combining 2 numbers in a particular way to get a third number. All of the calculations that you see on the page are the same thing, right? You have operation in between 2 numbers, and then you get a third number, right? Now, obviously, since this one is different, uses letters, and you are terrible people, you discriminate all the time, clearly log is not going to be, right, equal to all the others as operation. Or maybe it's just that it's learned so late in life that you just completely don't care about it. But that's what the log is. It's just a way to compute things. Log is not a function. Log is like addition. It's just you do something, right? So, what is log? Well, log is, as you can see, an inverse, one of the 2 inverses, for exponentiation. Addition and subtraction are inverses of each other because they undo each other. Multiplication and division are inverses of each other because they undo each other. And then, obviously, log and exponents are going to be inverses of each other because they undo each other. And that fact gives us the most important formula, conversion formula, for logs. This is all pre-calculus 1 still. So a raised to the power b equals c converts into log base a of c equals b. This is conversion formula from one realm into the other. Now you use this to compute equations, logarithmic and exponential equations, which are actually important part for your application problems, especially obviously in pre-calc 1, chapter 3, and then we will see in calculus 2, we are going to take this lecture in calc 2 and make it and marry it with word problems. So we'll do some derivatives on top of everything we do here. So now, how do we use this? Well, let's say you have to compute 3 to the x minus 7 plus 9 is equal to 24, right? Let's say this is the equation. You will use logs to solve this. So first order of business is to move 9 to the other side. You will subtract 9, so you will get 15. And now you are going to hit both sides with the log 3. Now, you are going to apply log 3. You don't multiply log 3 or anything like that. It's like, you square root both sides. You don't say multiply by square root, because that makes no sense. Square root is operation. You can't multiply by operation. You will not say multiply by times. That's, yeah, right? So, we are not multiplying by log because log without an argument is just this, right? You have to have something after log. So we apply log base 3 to both sides. And the reason why we apply log base 3 to both sides is because exponential and this one will cancel, and we are going to get just x minus 7 on the left-hand side. But we are stuck with the log base 3 of 15 on the right. And that we have to use a calculator and change of base formula to change these things and make this thing work. So here's another useful formula. Change of base, where your log base a of b is equal to ln b divided by ln a. This is the change of base formula. This is calculator related because your calculators only speak base 10 and base ln, base e. So now I'm going to go into the because if I can find it, there it is. And I'm going to type in ln 15 close parenthesis divided by ln 3 close parenthesis and get x minus 7 is equal to 2.465 to round it, and then I will add 7 to both sides to get 9.465, and that's the answer to the question, right? I had the exponential equation and I have the answer. Now, right, if you care, you will take that answer, plug it up there, and make sure that it works. So let's do that in the calculator. I have 3 raised to the open parenthesis. X is 9.465 minus 7, closed parenthesis, and then I have plus 9. When I do this, right, as a check, plug in, x equals 9.465. It works out as equal to 24.00043636. So this is all of the decimals that I get. Well, yeah, that's 24, okay? Because some rounding has to happen because I cut off infinitely many decimals over here. So clearly, you are not going to get exactly 24. But if you care, right, you would definitely plug in the value you get back in the original equation and so on. So we can, as you can see, use logs together with a change of base formula to calculate logs. Your calculator most likely do not support plugging in. I know there's one of those scientific calculators like TI 30 something, where you actually can specify the base for logs. But any serious calculator will have only base e, which is ln, and base 10. So let me write those down now. So if you have just, let's say, log of 3, that means log base 10 of 3. If you have ln 3, that means log base e of 3. So these are just shorthand, lazy notations so that we can deal with things. So that was the introductory part. Now I'm going to take logarithmic calculation and make it into a function. And we do that by simply getting an x in there. Look at here. When you are looking at this calculation table, which I created, all of that is arithmetic. Arithmetic is the art of computing. And many will say, not math, okay? It's just computing numbers. But then, what I can do to make these things function is I can go and change any number into x. As soon as I do that, they become functions. I can have x plus 3, I can have x minus 3, I can have 5 minus x, I can have 2x or 3x or 6 over x or x over 6. Or, I can have any of those combinations, right? But as soon as I introduce x, these basic calculations turn into functions, because now x is free to take on all of the values from the domain, creating not just one answer, like over there, 5 or 2, but creating the whole family of answers, infinitely many answers, because you can plug in infinitely many x's, and that will generate infinitely many answers, which is actually shown in a graph. So now, what do I do with the log function? Log function, y equals, right, f of x is going to be log base a of x. And now there are specs for that, right, all of the things, one of which is the graph. The graph goes like this, going through number 1. So this is the graph of log x. Now it's not humanly possible to do an amazing job in graphing these, because these are all ferocious decimals forever, all right? There are certain things that you can do. So the adjustments would be like this, right? You have a log of a bigger number, it will go like that, or log of the smaller number will go like that, right? It's all the same shape, so who cares? So what is our domain? Domain is going to be 0 to positive infinity. We are not including 0 because there's a vertical asymptote there. Range, as you can see, is from negative. You want my lenses? No? Okay. Can't see anything. Okay. Great. So these are the basic specs, and we are done, almost done, with your pre-calc review. What follows are the 3 formulas that you need to master to be really, really good with the most powerful derivative taking technique. Coming right up. So let's see. Formulas to expand or compress when you have multiple logs given. You can use log, you can use ln, you know it's all the same, doesn't matter, so let's use ln's. ln of x times y is ln x plus ln y, so that's number 1. Number 2, ln x over y is ln x minus ln y. And number 3, ln x raised to the power p is p ln x. So these formulas are very important. How do they work? Well, let's go with expand, because that's the one we need for calculus class. So expand ln of 3x y to the 5 divided by z minus 1. What do you do? All right. You have multiplication on top, 3 different factors, and then you have subtraction in the denominator, but that's only considered 1 factor. So what is this? This is going to be ln 3 plus ln x plus 5 ln y minus ln of z minus 1. So you can't break that one apart. And I'm going to leave it here so you can stare at the rules and stare at the answer. You must be able to do this in this class. I'm not supposed to talk about this. I'm just supposed to tell you recall and use it. But gotta know this now. So in pre-calculus, You learned this formula in pre-calc 1, and then they said you use them to expand or to compress. And the only ones you used in the pre-calc 1 is compressing them, because you need to compress to solve equations. But now in calculus, you want to expand to do derivatives. And that's why we want this. Yes?
If you would like
Negative 5, we would put it down.
1 over.
Well, yeah, we will go here as a multiplication, so it will pick up a negative in front. Right? Also, think about negative 5, it will be negative 5 over here. Either way. Let's do one more example of this. Expansion, and then we can go and do calculus. So anytime I lose wireless signal, I don't know, it's really moody the last 2 weeks. See, everything immediately doesn't work. As soon as the spring break kicks in, like after that, student brain dead, internet brain dead, like everything. I lost the will to live by that time. So, I see my Calculus 3 class twice in 3 weeks. 2 snowstorms, 2 Wednesdays done, right? So I saw it anyway. And one of the Mondays kind of in the fall after the class. There we go. Yay. So, to expand this, we are going to have cube root is the 1/3 as the exponent. So we have 1/3 ln of x plus 1 in parentheses plus 6 ln y minus ln of z minus 3 minus 8 ln w. Generally, you have an issue with this minus here, but it's a minus because it's divided by w to the 8. And then you will say, oh, but there's a times over here. Yes, but then this minus distributes because it's minus for every term. You can actually do parentheses and put that plus if you want to. And then when this minus distributes, it will change it into a minus. Whatever way you want to do it. Okay. It's minus there. And you'll figure out pre-calc 1. So those are the skills. That's the review from pre-calc 1 on basic logs. And now it's time for us to do some log derivatives.
Yeah!
There we go. Oh my God. Like pulling teeth. So, basic definitions. The derivative of ln of x is 1 over x. Now we make it spicier. What is the derivative of ln of any function? And that would be the derivative divided by the function. You will be using this formula 99% of the time, okay? So 99% of the time is that formula right there. And then we can make this the most general case we can possibly think of And that's going to be when we have any base in a log, because all of the ln's, they are just base e. But you can have base 2, base 3, base 3.7, whatever. So the most general formula is the derivative of log base b of any function. Right? That's the most general formula you can get. And you have the same like above. So it's f prime over f. And then you also have times ln b in denominator. So that is the most general case. But as I said, 99% of the time, for all of the problems you do in Calc 1, 2, 3 differential equations, you guys are going to use the formula here. Now, depending on how advanced your other classes are, right, like physics and chemistry and so on, you might run into the derivative of base 10, right, in which case you have to use this. You will have ln 10 every time you take the derivative. Earthquakes, sound, all of that stuff, pH values in chemistry, so they all have log base 10 calculations. So now let's take some basic derivatives so that we can talk about the coolest one.
Get the spray. Get the pancakes.
Yeah, you're right. All right. After the class is over, it's either going to be slash tires or a dinner. It's like one or the other. Those are the two options. Derivatives. What is the derivative of ln of x squared plus 3? So after exponential functions, taking derivative of logarithmic functions with ln is the cheapest thing you have in calculus. Because look at the formula up there. You are supposed to take the argument as is and put it in the denominator, so that's x squared plus 3, and then write its derivative on top and walk away. That's all it is. It's the 99% of the time formula, right there. You take f of x as is, put it in the denominator, and then its derivative on top. And you're done. Next example. What is the derivative of ln of, let's say, cosine to the 8x? We can do that. Well, I hope you remember the P formula from pre-calc. That's going to come in very handy in this problem because it will kill the chain rule. Whew. Look at this. The derivative of, and then that exponent goes in front of ln. And this just becomes 8 times ln cosine x, whose derivative is, write the cosine x in the denominator and put negative 8 sine x in the numerator, because the derivative of cosine is negative sine, right, which goes for f prime, and then you had the 8 as a constant in front. So the whole thing is negative 8 tangent x. So what's the derivative of ln cosine to the 8x? It's negative 8 tangent x, which is great. It's awesome. Let's take the derivative of ln of fifth root of, I don't know, x to the 6 plus 3x, whatever. You're going to do the same. This fifth root is 1/5 in front. So we have the derivative of 1/5 of ln of x to the 6 plus 3x. So that is, you copy the constant, which is 1/5, and then in this fraction, you have your x to the 6 plus 3x down there, and you have your 6x to the 5 plus 3 up there. You can factor 3, so you have 3/5 in front. On top, you have 2x plus 5, no, 2x to the 5th plus 1, divided by, you can factor out x in the denominator, get x to the 5 plus 3x, no, plus 3. And that's the most simplified version. That's the most simplified version. So what is the trick? In the last two problems, and I have them both displayed currently, in the last two problems, my entire argument of the log was raised to exponent, in this case 8, in this case to 1/5. I used the basic pre-calculus formula to kick those in front of ln. As you can see, there's 8, there's 1/5. That killed the chain rule. You see the power of logs? It's so good, right? It's really good. Now, can I force and really make chain rule problems? And yeah, I can, right? But, Okay, let's take a look at more derivatives. Right, let's take a look at logarithmic, yes? What do you mean, no? We're going to look at logarithmic differentiation, is that okay? Oh, okay, good. Whew. So now, let's take a look at the derivative of 3x squared minus 1 raised to the 6th power times the cube root of x to the 5 plus 2. Well, everything divided by 3x to the 4th minus 1, everything to the 4th power. Real quick. So what do we have here? To find this derivative, what do we need to do? There's no ln. So what do we do when we see a problem like this? Other than walking away, obviously. That's always an option. Cry, okay.
You asked to check. You asked to check. What's that?
Oh, you asked check? Do you understand that there is someone at the other end looking at this and saying, really? This is your question? Nope. Can't, right? What do we have on a pile? Guys, look at it and tell me, what do we have on a pile? What do you see? Quotient rule, thank you. And then, as you have to take the derivative of top, what is it? Product. And each one of these factors is? Chain rule. Great. So you have a product embedded in the quotient, and anytime you take any derivative, you actually have chain rule around. So to take this derivative, it should take about 20 minutes. And then probably simplifying it another 30, 40, right? So it's an hour. So that's an option. Or you can just look at the problem like this or any other problem we ever had and just write the derivative. Just write the answer. Skip all the work. Skip all the rules. Skip everything. And just write the answer. In factored form. Wow. So let's do that. So what's the derivative of this? The derivative of this is you just copy the whole thing as is. So 3x squared minus 1 to the 6th times the cube root of x to the 5 plus 2. Everything divided by 3x to the 4 minus 1 raised to the 4. Right? So that's how the answer starts. So you copy the entire problem times, and then we have another part that you guys have to learn. So what's in this other part? In this other part, we are going to have 3x squared minus 1, and then that's 36x on top, plus 5 thirds of x plus 2 goes in denominator, and then x to the 4th on top. And then you have minus, we have 3x to the 4th minus 1. And on top, we have 48 x to the 3. And that's it. That's the derivative. So we had the 3-chain rule, quotient rule, and a product rule, and that's the answer. When you factor, simplify everything possible, and if you are to actually do all of those rules, it should take a very long time. I could. Should I? Are you interested? Step by step? Good. How about we do it on a simpler problem first, because I'm going to write everything in between, and then we're going to learn the pattern. If you spend hours practicing this, everything else in this chapter, other obviously implicit differentiation, becomes irrelevant. Because this technique takes care of everything, and you saw me just plow through all of the rules, right, without actually writing anything down. I just wrote out the solution right away. So let's see what's the secret behind this method, and then what you guys, if you want to, what you could learn to be at that level. That's a car, right? Oh, it's okay. Sounds like a little boat or something. So, we have that little pond over there, so maybe in a circle. Actually, every semester, students go and test it for to see if there is any water in that pollution, and usually there isn't. Now let's take the derivative of something simpler than this craziness. So how about x to the 8 times x minus 3 to the 6 divided by the cube root of x squared minus 1. Right? It's just less writing. And you can literally put whatever over there. You can put trig, you can, just put whatever. Really? I mean, you would think it guy's fast, right? But apparently not. By now, I've been in New York. You got a ticket for being loud? Yeah. Oh, that's why you're quiet in class. Yeah. You invest $20 in a muffler, and then you have to invest another $200 for the ticket. I mean, whatever. All right. So there we go. Now, here's the method. Focus. Y equals, and then we put ln on both sides. Now, this next step is to expand everything. So, I have 8 ln x plus 6 ln x minus 3 minus 1/3 ln x squared minus 1. So all I did is those three formulas combined to expand everything. Now I hit this with the derivative. What do I have on the left? On the left, I have derivative of ln y is 1 over y. And then I have to follow with the chain dy dx because implicit differentiation, right? Now, on the right-hand side, the derivative of 8 ln x is 8 and then 1 over x. Because derivative of ln x, right, we had that as a formula. I'm going to scroll. There it is. You see this first one? The derivative of basic ln x is just 1 over x. All others will fall in the 99% formula. So the derivative of ln x is 1 over x. Great. The plus 6. The derivative of x minus 3, right? You put x minus 3 on the bottom and it's derivative on top. And then minus copy the constant 1/3. The derivative of x squared minus 1, right, with ln is x squared minus 1 in denominator and then 2x on top. So you see this y over here, right? That has to go to the right-hand side, and that's the reason why I was copying the function. Remember that? When I did the evil problem over here, I copied exact problem. Well, that's because of that y. You will always have that y when you do logarithmic differentiation, and it's going to go on the other side and multiply everything. So now you have y times 8 over x plus 6 over x minus 3 minus 2/3 x over x squared minus 1. And the last step is just to write the original problem instead of y. So the final answer here is dy dx is equal to x to the 8, x minus 3 to the 6, cube root of x squared minus 1, and then you just copy the bracket over here. 8 over x plus 6 over x minus 3 minus 2/3 x over x squared minus 1. So now you see all the steps in between. But did I actually do these steps with the problem up there? No. I know the pattern on how to deal with this. And I can, in my head, mentally decompose the second line where you have the derivative, the red derivative. I am able to decompose that line in my head. And then the rest is easy. So this is called logarithmic differentiation. And I hope you will agree that in the problem up there, you have a product rule in the numerator. The entire problem is the quotient rule. And then you have two chain rules, right? On x minus 3, there is a chain rule. And then also on x squared minus 1 is a chain rule as well, with a cube root. Have we done any chain rule, any quotient rule, any product rule in this procedure? And the answer is no, if you paid attention. So this method is extremely powerful because it really just goes around all of those other rules. However, you know, when problems are simple, you don't really bring a sledgehammer, right, every time. And this is technically a sledgehammer. Every time you have a very complicated, long problem that is going to take forever to differentiate, this one, right? You have a basic product rule with like 2 things. Do the product rule. You can avoid every single one of those product rules and chain rules and everything 100% of the time with this method. But then why would you? right? You can just do this for the very difficult problems, very annoying problems, and then use the, cute small rules for cute small problems. That's generally what it is. So let's take a look at the method one more time. Now, this time we are going to consider the basic product rule problem. So say you want to differentiate x squared sine x. Just do the product rule for 2 seconds and you're done. But let's use a sledgehammer because we can. All right? So what would be the product rule solution over here? Copy the first times derivative of the second plus copy the second times derivative of the first. And then you factor everything. You just get x cosine x plus 2 sine x, right? And that's if you do product rule. But again, we can set this equal to y, and then we can ln both sides, and then we expand into ln y is equal to 2 ln x plus ln sine x. That's it. And now you hit this with the derivative. Now again, if you learn the pattern, you wouldn't be writing anything. You would just write the answer right away and be done. But now we're learning, so 1 over y dy dx as a chain is equal to 2 over x. Derivative of derivative of ln x is 1 over x, and then times 2. Plus sine goes in the denominator and the cosine goes on top, so that's the cotangent right there. So what do I have? I have dy dx is equal to y times 2 over x plus cotangent. Let's write cosine of sine because we're going to replace stuff and then cancel. So let's leave it as cosine x over sine x for now. Now we're going to replace what y is. So dy dx is equal to x squared sine x times 2 over x plus cosine x over sine x. And then you distribute. So dy dx is equal to, you will take 1x inside parenthesis to kill the denominator here, so 1x stays. And then you will take sine inside. So it's just x factored out. X and x cancel, so you have 2 sine x there. And then plus x, and then sine and sine will cancel, so you just have cosine x. And if you compare that with the blue one on top, they are the same, except the terms are swapped. But as I said, you don't take the sledgehammer for the problems where you don't need one. Let's say you want to put a picture on a wall, right? Have a little nail, and then a 50-pound sledgehammer, right? So when you hit it.
What is this method called?
Logarithmic differentiation, right? You ln both sides. It's in the book, and hopefully in the class preps and everything else. Let's take a look. Let's take a look at the pattern. So say that I have to take the derivative of x cubed times square root of x cubed plus 1 divided by sine x. I don't care. I put whatever. How about x? No, you can't do x because they will cancel with a cube up there. So just leave it like this. What you are learning as a pattern is that you are copying the function as is, mid parentheses, So you copy function as is, which is x cubed, square root of x cubed plus 1 over sine x. And then over here in the parenthesis is the stuff that you get from the expansion. Okay. X cubed is in the numerator. So that would be ln x cubed. 3 goes in front of ln. So I have ln of x. Great. 3 over x. Because this term, x cubed, produces 3 ln x in an expansion. And because it produces 3 ln x in expansion, derivative of ln x is 1 over x times 3, 3 over x. Then I am moving to the next term, and I'm getting 1/2 x cubed plus 1 in the expansion. Right? I keep this in my head. So now what's the derivative of that? It has to be, since it's times in the numerator, it's plus. 1/2 is a constant which you copy. The function gets copied in denominator, and its derivative on top. Done. That's the next term. I didn't do any chain rules and stuff. And then the last term is in the denominator, and it's sine x. So that one is going to be negative. Sine x. Great. So negative. Put sine x here, and the cosine x on the top. Right? Because the derivative of sine is cosine. And we're done. This is the derivative. Now you can go and make it prettier if you can, and you do. You can put this 3 over here, and you can do cosine over sine is cotangent. And you made it a little bit prettier. But as you can see, you go from the problem directly into the answer, but there is a condition. And the condition is that you have to be able to decompose this perfectly mentally, right? And if you can't do that, obviously, practicing it on a paper will help. You are not required to solve each derivative by looking at it right in the factor form and all of that stuff. No. But it's a good thing to, at least to annoy others. Yes?
Those intermediate steps that you wrote in place, you just put them all back?
Sure. So we had in expansion 3 ln x. We have, so positive 3 ln x. We have positive 1/2 ln x cubed plus 1. And we have negative ln of sine x. So those are the steps in the expansion those are the things that I keep in my head. So I look over here and I say that's times x cubed, so that's 3 ln x, so 3 over x, because the derivative of ln x is 1 over x. Then I go here, that's
So that
1/2.
That became 3 over x.
Yes, this is 3 over x, this is 1/2, blah, 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 and this is cosine over sine.
No, the 3 ln x, that became 3 over x.
Yeah, because you get ln for each one, right, in the expansion. Let's do more, because we can, because we want to. There are certain problems that can only be done this way, and nothing else works. Right, Daniel?
Yes, sir.
Good. So, do you know why I singled you out?
Yeah, because we were fighting about Android and iPhone.
Oh, wait, what's your side?
You see? I don't even want to say this right now. iPhone.
Wait, you are on iPhones? Get out. Actually, no, get out. So, let's take a look at problems that must be solved using this. So, for instance, what is the derivative of sine x raised to the tangent x? Right? Now, you probably go, why? Because we can. That's the only reason why. And for these problems, the only option you have is logarithmic differentiation. So what do? We go y equals, leave some space, sine x raised to the tangent x, and now hit both sides with ln. By the p rule, tangent x hops in front of the ln. So now I have ln y is equal to tangent x times ln of sine x. At this point, we hit this with the derivative because there's nothing that we can expand. You just have ln of sine x, so there is nothing to expand there. That's done. So all I need to do now is to just take the derivative. On the left-hand side, I have my 1 over y dy dx. Right, that was the implicit differentiation chain rule. I took the derivative of y in respect to x, so I have to follow with the chain. On the right-hand side, I have the product rule. And unless you want to do nested logarithmic differentiation, do the product rule, okay? So copy the first, which is tangent x, times derivative of the second. Well, that one is easy, right? You put sine x downstairs, and then it's derivative cosine x on top, because derivatives of logs are easy. You copy the function, the argument, in the denominator and put its derivative on top. It's always f prime over f. That's it. And then plus, copy the second, which is ln sine x, times the derivative of the first. Derivative of tangent x is secant squared x. So now, dy dx, y goes to the other side, and that is the original function. So that's sine x raised to the tangent x. In parenthesis over here, tangent is sine over cosine times cosine over sine. These guys cancel, because that's tangent times cotangent. Well, they cancel to 1. That's great. So I have 1 plus ln sine x times secant squared x. Ta-da! That's the derivative. And there's no other way to do this. You have to use logarithmic differentiation. So when you have these guys, exponent of the exponent of the exponent, this is what we have. So I want to do one problem from the book, and I hope you're not disappointed. The lecture is over. We have exponential, we have logarithmic derivatives, and then logarithmic differentiation, which is when you ln both sides, expand, and then do the stuff. Hold on, Chewbacca, I'll find it. All right, here's the one. So we have the derivative of x raised to ln x. So this is problem 46. So y is equal to x ln x. I'm immediately going to hit both sides with ln. And then have ln y is equal to ln x times ln x. Hey, that's ln x squared, right? But this is where you have to be careful. This is ln x squared, not ln x squared. So this 2 is not going in front of ln. When you have ln x squared, that's 2 ln x. But if you have ln x squared, well, that's it itself. There's nothing new there. It's just ln times ln. So you can't put 2 in front. You have to be careful about that. Hit this with a derivative now. And we have 1 over y dy dx. And on the other side, I have the basic chain rule. So 2 ln x times the derivative of the inside, which is 1 over x. So dy dx is equal to, move y to the right, which is x ln x, times 2 ln x over x. Ta-da! So that's the 46. We already did a very similar problem to 49. I had sine raised to tangent, or tangent raised to sine, whatever I had. They have sine raised to ln. And then the next problem, tangent x raised to x minus 1. You know what we didn't do yet? Tangent line problem. Yes, very good. So you get the problem like this, and now I say, what's the tangent line at 1? Then you go and you plug in 1 into this calculation, you find slope, and then oh, you want to do that? Sure.
I'll be back in a minute.
I hope you're not disappointed, but that's it. Exponential logarithmic differentiation. I don't have a closer, so